Thank you for inviting me. Nice part of the world. When you just look this way, if there was not for the palm trees, it feels like a little bit like Switzerland sometimes. So, I'm going to first give you a little bit of context. Engineering in Canada is a regulated profession, which means quite a few things. From the very mundane, you cannot claim that you are a software engineer if you don't have a license. You cannot put the word engineering in the name of your company and register it if you don't have professional engineer staff in that company. So it's a little bit different also from another perspective. In Ottawa, there is no Ministry of Education. There is no central way of deciding from the government perspective what should be taught. This responsibility is really distributed across the country. So, on another hand, the profession is very, very strong. The 200,000 or so professional engineers are organized across the provinces and at the federal level in an organization called Engineers Canada. So, by law, Engineers Canada regulates the profession, which means that it decides what is an engineering degree, what should it contain, and I look into that a little bit. What is this strange notion of having a license, pretty much like a physician needs a license to practice medicine. And a few other things like disciplining people who do bad things. Well, it's not necessarily going to the government and the police, but the profession is the first line of slapping people on the hand for doing bad things. And this didn't start with us software, it started with civil engineers and the bridge on the St. Lawrence River, which collapsed twice during its construction in the 1915s and 1920s. So the key motivation behind this regulated profession is primarily to protect the public. We trust our government to do the right thing so that the bad people don't do bad things to the citizens. So there is a concept, and you may have heard the term PE, professional engineers in the US, or CE, chartered engineer in the UK. While we have PEng, so I'm a PEng. I have a license to practice engineering. So how do you get a PEng in Canada? Well, you get a PEng, there's quite a few conditions. You need to have a degree from, an accredited degree from an engineering school. Well, since there are immigrants, we will also look at other degrees and scrutinize them and see how they balance relative to the Canadian standards. And then, that's not enough. It's not because you have a degree, that's it. You can put engineer on your card and on the plate outside of your office. You need to have 4 years of demonstrated practice, and in general, under supervision of a professional engineer that is himself or herself licensed. So, on top of that, there is some extra examination. Even if you did it 4, 5, 6 years ago at school, you have to go back to some examination about the laws that impact engineering and professional practice and ethics and quite a few things like that. So there's quite some hurdle to get there. But finally, you know, there's about 200,000 people who are professional engineers in Canada. So the thing that concerns us educators is this notion of program accreditation. Accreditation is some kind of a certificate that you put on a program that says, yep, this is conformant to the expectation of Engineers Canada, that organization of engineers, and your graduates, if they get the proper 4 years of experience, are likely to be licensed. So this is some kind of an examination that the various engineering schools have to go through program by program, and you'll get your accreditation. If it's a brand new program, you'll get it a temporary one for a year, and then you may get it for 3 years. If it's something that is solid, well established, you get it for 5 or 6 years. So this is not done, again, by some kind of central government bureaucrats. This is done by your peers. So it's other engineers and other engineering educators from across the country who will look at your program and decide about accreditation and for how long. Now, until 2014, This was done by looking at the program, looking at the curriculum and how many hours you would spend on this and spend on that, and the quality of your educators, and the kind of exams that the students would go through. So it was basically just looking at the curriculum itself. But in 2014, there was a massive change. Engineers Canada has decided that they would look at not so much the program. Well, we can have a look. We want to see what comes out. So it's outcome-based accreditation. You know, the Engineers Canada says, okay, show us that the people that come out of your program, they're useful for industry. They know something. So it looks, you know, pretty trivial. You know, we thought, well, we were doing that before anyhow. So this outcome-based assessment, the CAB, Engineers Canada, decide what we should measure. But they don't tell us how we should measure it. Each engineering school was left to decide how to demonstrate that we have the proper outcome. So we also need to demonstrate some kind of evidence that this outcome is not just some report that we send them, but that we use that in some continuous improvement for the program. For us, software engineers, this reminds me a little bit of the CMMI. You know, basically, the previous system, we were all sort of level 2. Now we have to demonstrate that we are level 3 or 4 or 5. So we have to put some assessment process inside the organization that is not just sending all the details of all the courses to some big office somewhere in Ottawa. So this assessment process, it's pretty typical of what we do in other disciplines. We need to establish some clear goals, we need to establish some metrics for this goal, we need to collect the metrics, and we need to reflect on the metrics and decide for some action. So the typical loop that we see in software process improvement and that kind of thing that we're familiar with. But what is it that we have to measure? And that was the big surprise and the big shock for a lot of educators in engineering school. So here are the 12 graduate attributes that we have to demonstrate that we achieve this in our students when they exit the program. So the first 5, they look pretty familiar. Okay, we have to teach them quite a few things about, you know, the basis of engineering, you know, all the good math, you know, differential equation and some basic physics and all that kind of good stuff. And we have to tell them how to design. And okay, so this was not too much of a surprise. You know, a knowledge base for engineering is the first one. You know, all your good basics that you do in year 1 and year 2. And then how to do problem analysis and how to investigate, you know, possible solution and balance them and have criteria. Pretty easy, would say every prof, you know. I've been doing that for 20 years. That's what my exams are about. That's what I looked at when students send a report or whatever. Doing design, yeah, it's an engineering school, so that's what we're about, you know, doing design, making choices about how to build products. Use of engineering tool, pretty easy, you know, UML, model-based driven stuff, Jira, you name it. We use all those tools. So that shouldn't be a big issue. Well, the next 6 are a little bit more puzzling. Individual and teamwork. So the ability of our students to work in teams, not necessarily in teams that are very homogeneous, interdisciplinary team too. Communication skills, you know, oral communication, written communication, other kind of media literacy. That's also something that we sort of take a little bit for granted. And then professionalism. How are we going to fold that into the curriculum? You know, impact of engineering on society. Yeah, sustainability is a word that comes and again and again and again over the last few years, at least in my engineering school. And then more exotic, you know, things like ethics and equity. Ethics and equity. This is an engineering school. This is not an art school. So, economics and project management. Okay, that project management and a little bit on engineering economics have been part of the tradition for many years, and it's something that you can somewhat assess also by examination. Although project management, how are we going to do that? We cannot have each student manage a project. This one was the most puzzling. Lifelong learning. Well, they're here to learn. 4 years, 5 years, not lifelong. That's after when they leave. Well, how are we going to prepare them to that lifelong learning? What are we going to give them? So these soft skills, as we used to call them, well, when we have to actually demonstrate that our students have acquired them, it's a little bit harder. And actually, I look forward for a presentation this afternoon to see, get some new ideas there. So inserting them in the curriculum in a meaningful fashion, yes, we can tell students you'll have to make some presentation and you'll have to write stuff. But how do we assess that their progress on that and they achieved a certain level of competency when they leave the school? So that has been a big hurdle for all engineering schools in Canada over the last 2 or 3 years. So I'm in a big electrical and computer engineering department. We have about 900 undergrad students in the department and 57 faculty. So it's been quite an enterprise to put that together. So we had to look at those attributes and go to 1 or 2 level of decomposition, decompose them into more attributes, and then for each of the attributes, try to see how can we assess them across the curriculum from year to year. So we had to develop rubrics, and we had to sort of do a mapping of all these attributes to the various classes that we had, and then distribute to the profs some spreadsheet to collect the data. So we already had to grade students, and that's a painful thing to do, and it's tedious. And now we also have to collect data, not for the student, but for that humongous database that will allow us to ultimately demonstrate that we've achieved the 12 graduate attributes. So, yeah, we went through this exercise of breaking down those 12 attributes. So the first 5, easy, we had all kind of data to do that. The last 6 that I listed, yeah, they were quite puzzling. Lifelong learning, how do we do that? What do we check at the end of first year? What do we check at the end of third year? In which course is that? Lifelong learning in the math course? Differential equation? I don't know. So people were really puzzled. It's not that we don't see the value of these attributes, but how do we assess that? So we had to do a big mapping, all the courses laid out, and each of these indicators, try to map them. So we could do a little bit of that check in that course in first year, and some of the check in that course in the second year, and so on. And then we produce rubrics. Okay, that's not legible, but basically, a list of criteria to assess the competency of students. So we went through that exercise, pretty long, painful exercise. Took probably 2 years to set it up, to give you an idea of the order of magnitude. And then some distributed work pushed on every single prof in the department. There was actually some immediate benefit to the program. Just doing the exercise of trying to collect all this data triggered quite a lot of discussion and changes in the program. Especially when we were left with some attributes that we had no clue. We all felt like, yeah, this is valid, but who's in charge of that? In which course do we actually do this? So indicate that to the students and evaluate it. So the first reaction was to sort of not front load, but back load. Oh, in 4th year, we need to add a lecture on this, and we need to add a quiz on that, and we need to add, so there was a lot of backloading of the program, just in order to make sure that we would cover at least, 80% of our, couple of hundreds of attributes. And then we started to identify other gaps, things that where we decided, gee, we cannot just check this in the last 6 months, in the last term. We cannot plug a lot of things in courses in 4th year just in order to be able to measure these attributes. We start to have to flow things down in earlier years. And we have to make sure that it builds up from one course and 1 year to another. Which forced prof who actually never spoke to each other to start speaking to each other. So you're going to cover this in the 2nd year, and in my course I'm going to follow up on that in the 3rd year. And by the way, we're going to hand that to Philip, who's going to organize some big capstone project for the students in 4th year. So this created a few hundred meetings of faculty, and those are interesting, especially if you, like me, come from industry. Academics have a strange way of driving stuff with funny rules like Robert's Rule of Order and voting for things, but okay. So pushing things down into the curriculum has been an interesting exercise. One thing that a few engineering schools have discovered is the value of significant projects. Especially in my department when I arrived, and that was one of the tasks that I took over when I joined UBC a few years ago, was to make the project that students do much more significant. So we have projects that are year-long, where groups of students do some engineering work for a company in town. Each project is different, it's not all groups doing the same, so we have about 70 groups working for about 50 different companies. So it's quite an endeavor, but it also allows us to evaluate quite a few of the attributes, especially in the last 6 sections, about how students behave professionally with their industry partner, communication with the industry partner, issues such as intellectual property, non-disclosure agreement, and all that kind of thing. They face it for real. It's not just some slide on PowerPoint in some course. They have to sign a non-disclosure agreement with their partner and all that kind of thing. They have to involve the university lawyers in the process and so on. And this is done under supervision of a professional engineer, which is not necessarily a prof in the department, but somebody, I have a few other practitioners from industry who supervise the students group. But how does that apply to software? So some of my colleagues in the little group that we are that focus on software engineering in this big electrical and computer engineering department, we sort of said, well, maybe software developers, not software engineers, we cannot use the word if they're not engineers, software developers, why would they need a license? Why are we punishing ourselves with this humongous amount of work for something that maybe our students couldn't care less? If you are a civil engineer like my daughter and you are not licensed, basically you don't have a job in Canada, or you can just work as a technician. But you cannot put your seal on the blueprint on something. But in software, who cares? So that has been a big debate over the last 5-6 years. Should we look at licensing of software engineer? Some people in the department say, maybe we don't need an accredited program, and we'll still have plenty of students rushing to our program. What we need is a good program, but not necessarily one that is accredited. However, the world that I come from is full of things that where actually the quality of the thing matters as much as the quality of a bridge or the tailings of a mine. So maybe we should care for at least a subset of the software project that software developers are involved in. I worked for many years in transportation. The little picture here, that's the subway in Vancouver. People are always surprised when they arrive in Vancouver, there's no drivers in the train. I remember a kid said on the platform in the airport, "Mom, they forgot the driver in the train." And the kid could actually take the place of the driver. You can sit in the front and pretend that you're driving the train. Yeah, all the trains are automatic. Biomedical instrumentation, nuclear power plants, and all that kind of thing. Well, that's what I call software that kills. Plus, for 10 years of my career, I've been on the other kind of software, the software that kills but kill the bad guys and avoid killing the good guys. But there's more than that. There's more than software that kills. There's a lot of software that touches relatively large amount of liabilities, financial liabilities and things like that. So, Mr. Mark Galliot was evoking the fact that small companies and large companies depend completely on software. I mean depend. That is, the business stops and you start bleeding money if something goes wrong. So when we look back at the reason why we have professions organized as professions and in some countries like Canada regulated, it's mostly to mitigate the risk to the public. We cannot eliminate every risk and make life completely risk-free. But we can try to limit the damage, and we can do that without having the government involvement, but maybe by having the profession organizing itself. You know, there's, you know, the regulated profession is the third logic in the words of Freitzan. We can have the market regulating things. If people produce bad software-intensive systems, people will stop buying them. Well, but maybe it's too late. Maybe you've done the damage. So we cannot just rely on the rules of the market. You know, I was just last week in Netherlands, and the Dutch government has suffered in the last few years from quite a few disasters in software development. There's the Obamacare system that also is mind-boggling when you look at the kind of decisions and engineering decision and project management decision made behind it. Now that some of the details start to surface and a report was issued, you would think, who in his right mind, with an engineering sense, would actually take responsibility for this? So we could, and some countries have tried to do that, have a huge bureaucracy and basically put a policeman behind every software project, not to hit every software developer. But the relatively elegant balance is what I described earlier, this notion of having the profession itself regulate itself. So what is a profession? A profession is a body of people who share that relatively specialized body of knowledge and define a certain set of competencies. This competency you acquire it in two forms. You acquire it through education, whether it's formal education in a university, for instance, or an engineering school, or a medical school, or something like that. And then complemented by actually demonstrated experience. That is, you don't just remember everything in the Bloom's taxonomy, but you can actually do it. This comes also with duties and responsibilities towards your peers, towards your employer, towards the public at large. You know, we speak about citizen engineers a lot recently. Usually professions establish their own codes of conduct and their own rules of ethics, which more precisely specify what you can do and what you cannot do, or what you should do and should not do. And then in some respect they also do a little bit of advocacy for the profession. We are the good guys, you know, trust your engineers to do the good thing. And other professions do that to accountants and physicians. So this concept of a profession is not new. It actually, somebody told me it originated in India some 2,000–3,000 years ago. It became very visible in Europe in the Middle Age. You know, the people building cathedrals and things like that were really organized in professions in various disciplines, and they had this notion of learning through apprenticeship or more formally, and then working under supervision of a professional in their chosen discipline. So do we have a software engineering profession by the criteria that I just described? Yes, sort of. We have a body of knowledge. I'm glad that I participated to the first issue of the software engineering body of knowledge, Rational Software, and my group was one of the sponsors. We have some standard curriculum now in software engineering. It's been developed by ACM and IEEE. We have in some standards of conduct, there's an IEEE ACM code of ethics. The British Computer Society has a much more elaborated one, and a code of conduct for engineers. And there are professional organizations looking at the qualities and education and continuing education. So two things do seem to exist. So it looks like, yes, we have an embryo of a software engineering profession. But, you know, there are issues, there are some concerns, you know, people say ethics, you know, why does it matter? You know, it's not like we're, again, building bridges and things like that, you know, so we need to put more of that visible and, you know, put it in the bottom neurons of our software engineers and relatively early in the curriculum. It's not something that they'll they'll sit for a little exam in 5 or 6 years and tick a few boxes. People sometimes say, well, you know, there's laws. If you do something illegal, you just go to jail or pay a big fine. But in software, I have to say I'm not very impressed. You know, we are a profession where people do all kind of strange things, and with all kind of good excuses or good excuses. Well, everybody does it. You know, I was in a hurry. You know, it passed all the regression tests, so I'm probably okay. You know. Well, beta version, isn't that for the customer to try it out and tell us what they really wanted, you know, so I'm used by seeing products that are in beta version for years and years. Well, you can do that. Would you imagine having a nuclear power plant that is in beta version for a few years? So there's all kind of things where software people tend to think that ethical rules and professionalism is for the others, but in software, because we have all these precedents, we can dispense from them. Another thing that software people tend to dismiss is this notion of sustainability. Hey, this is just software, it doesn't use much energy, you know, doesn't damage the environment. Well, we have to look beyond just software. You know, software is usually embedded in some much larger system, and we have to look at whether things are sustainable from the triple bottom line view or just technically sustainable. Mr. Marie Elliott was mentioning maintenance. We are going to suffer in the next few years of a serious maintenance crisis. Look at the amount of software that we develop. We cannot keep up with it. We'll have to develop less software and more reusable software because we just cannot maintain all the software that we are developing. So sustainability and a few other things like that, they do matter for software engineers. It's not something that we can dismiss and say, oh, system engineers or people that deal with the environment or people that deal with natural resources, and that's their problem. No, it's our collective problem too. Then there's another tension there, which takes different forms across Canada depending on how the universities and the engineering schools are organized. What's the difference or the commonality between computer science and computer engineering? Actually, software engineering, sorry. And well, computer engineering would be a third leg there that would be interesting to contrast. But I'll stick to software engineering for now. As I gave you a little bit of a hint in software engineering, if we want to be compliant to the demand of Engineers Canada, we have to stress, you know, all the good fundamental stuff, including continuous math and differential equation, one of my favorite, thank you very much. Physics, chemistry, statistics and probability, and engineering economics and project management and things like that. So, well, in computer science, they can certainly spend more hours since they can dispense with the differential equation and the project management and the engineering economics. They can spend more time looking at how compilers works and formal methods and model-driven stuff and architecture-driven stuff and all this good stuff. You know, because in 4 or 5 years, there's only so many hours that you can dedicate to teaching stuff. So some balance has to exist. And the spirit end up not being the same. Computer science tend to be focused much more closely to the code and the mechanics of the technology, whereas software engineering, at least in engineering schools, tend to be more focused on producing products. And the code is just one way to have the product, but it's not the main artifact. And I like your introduction. Yeah, that's where you look at deployment and all that kind of things. So this also creates another problem, is that now that we have licensing of software engineers in Canada since 1998, I know I was the very first one in June 1998, people out of computer science would like to get a license, and that's where they realize that, gee, their curriculum is missing. There's quite a few holes there, so they may have to go back to school or get a few extra classes to compensate some of the gaps in their academic knowledge. Not that they don't have the proper experience. Maybe they are good software engineers, but the licensing rules are such that we have this tension.
This is very strange, because if they are good, maybe the licensing process is bad.
Yeah, this is why we also look at a competency-based licensing process that has less focus on what kind of degrees you had, but more on what kind of competences you have. And we've tried
good engineers.
Yeah.
Then you say they cannot get a license. This means that.
Yeah, but so there's you know you need to have a discipline process that you can apply at the level of a whole country. It's precisely the crux of the problem is how do you assess that they are good engineers? Because they come and say so, or because they have a few buddies that write reference letters. Maybe we need to have a process to do that. My point is that just relying on a degree may not be the right way of doing it. Having a competency-based assessment is the way to do it. This will roll out in Canada, but slowly. Software engineering is not the most, important discipline. This is being rolled out for electrical engineering and civil engineering in priority. But I agree with you. We need to get to answering the right question, not using the wrong instrument to answer that question. So I'm all in favor of, yes, the concept of licensing software engineers and the fact that we probably, when some critical mass will have been achieved, to do what happens in other disciplines, in other kind of project, to demand that professional software engineers be involved in certain project. Which doesn't mean that everybody in a project has to be a software engineer with a license, but somebody has to take responsibility for it. Pretty much like in other engineering projects, not everybody needs to be licensed. This licensure needs to be on demonstrated competency and not just an exam. Exactly the point that I was making before. So in Canada, we are boldly going there. I'm not sure exactly what's happening all around the world. We have some good relationship with another small country that seems to have the same ideas, engineers in New Zealand in particular. And in Australia, there's also a push to go there. Our big brother from south of the 49s hasn't really got his act together except for the state of Texas, but okay, someday they'll get there. The ABET accreditation mechanism is also based on some attributes, but it's not as strong and rigorous as what Engineers Canada is trying to achieve. So hopefully we'll end up in some year, not in a too distant future, to a more mature profession of software engineers, which are more than just good coders, who are really engineers that can look at building complete products in a sustainable and ethical way. But also we need to produce a workforce that is versatile and nimble and able to adapt. And this is what the mysterious attribute number 12 is about, lifelong learning. We need to stop telling people that's the solution, this is the way to do it, this is the process you follow. No, this is our solution, this is our process, this is one good method. But things are going to evolve. You need to understand, you need to be able to analyze, put things in a proper context. So we need to give them the tools to actually understand what kind of gaps there are, what kind of new ways of doing things will come up. Especially, and this may be a little bit another perspective than that of Mr. Margaliot, we are moving in the software engineering to more of a contingency kind of workforce, workers on demand, where everybody is its own company and you sell yourself to different projects that may be not located where you are, where as a project manager you assemble a team with 6 people from Vietnam, which may not be your employees, they're just freelancers, all of them, and you assemble teams as necessary. So this will require a workforce that is much more prepared to be adaptable and to maintain its competencies as you go along, and not people who sort of say, well, I need lifelong employment, I have this good degree and a master degree and I know all the good recipes. Just give me an opportunity to do them for the next 30 years. It's a few years ago I wrote a little tongue-in-cheek paper speaking about the half-life of good software engineering ideas, and my hypothesis was it's about 5 years, and somebody did a more rigorous study than my little tongue-in-cheek paper and said, yeah, it's about 5 years. So whatever we know about software engineering, half of it will be obsolete in 5 years. 75% will be obsolete in 10 years. Most of it will be obsolete in 25 years. There's only a few things that I've learned at school that are still valid today. And they're mostly discrete math and that kind of thing. So anyhow, I'll leave it to that for now, and I don't want to impinge too much on the coffee break. And there's probably all kind of interesting, I looked at the program today, there's all kind of thing that seems to rhyme with my own presentation. Thank you.
How many licensed software engineers do you have in Canada?
Across the whole country, I don't know, because it's organized by province. Province is the equivalent of a state in the US. In BC, last time I checked, which was a few weeks ago, we were 53. In Ontario, they are probably about 4 times that number.
What percentage is it of the total engineers?
Oh, there's 200,000 engineers in Canada, so it's...
No, the software, percentage of the software.
Oh, I don't know.
No. It's a small number, right?
It's a very small number, the people who have a license. This is why I say there's a sort of chicken and egg problem. Big companies or governments cannot demand that there is a professional software engineer.
This is from a process that started at 98.
Yeah.
Something is wrong here, no?
I don't know. Well, there is no way to mandate that at this stage. But yeah, the kind of thing that's slowing it down is that a lot of the software developers that we have come from computer science departments.
You mandate all the other engineering disciplines. Why doesn't it happen in software engineering?
Because a lot of people say the same rules do not apply because we do not endanger the public. And we relinquish our responsibility on the end user. You know, when.
So one big catastrophe will solve it.
Yeah, I'm not sure. There are catastrophes already. If you look, for instance, at that Dutch report that I saw last week, the catastrophes do occur. It's just the path to legislate and regulate everything is not something that happens instantaneously. There's a lot of change that needs to happen in a lot of places, in education in particular, in the way procurement, bidding contracts are spelled out. This is not going to happen pretty rapidly, I think. But I don't think that the process is wrong. Things, you know, we didn't get to a professional civil engineer in 2 or 3 years.
If I look at engineering, civil engineer, when I design a bridge, I can look at the rules of physics and say it will stand that much weight, that
Absolutely.
much weight, and
That's
sure physics will prove the bridge will stand.
That's one of the difficulty in software engineering, is that we do not have the equivalent of the fundamental laws of physics to just look at our blueprints and decide that it's safe and that it does the job.
A lot of the business we do, about $1 billion, is from software testing. And what we found is that it's actually impossible to create a bug-free software. You'll always have bugs. You'll always have problems. So I think the nature of the industry, or the software engineering by nature, is a bit different than physics or civil, I mean, whatever it is, because it's the complexity.
Totally agree. Yeah, there are things that are not quite the same. So just doing a transposition that happens in a more physical domain doesn't always match well.
I have two comments. One is that software engineering is more similar to industrial engineering, where, again, you cannot use the laws of nature to do things. The other one is that Israel is the country of short range. And we say short range kills long range. Perhaps in software it's the same. Good software in the short range is too expensive. So companies that provide good software, it's too expensive and not successful economically.
Yeah, but economically there's other things at play, especially globalization, which was evoked by Mr. Margaliot, where there is some pressure to actually start, using the fact that we don't need huge investment to do software in a distributed fashion. So there will be some form of economic regulation to that aspect. But yeah, a lot of companies, especially startups, produce very, very short-range stuff. When we say short-range, they hope to just survive the next 3 months. But that's not the kind of systems that Margaliot was describing. Some software out there need to be resilient for many, many years. And it's not necessarily the super sexy computer science interesting stuff.
Okay, thank you for your